just like the first derivative can tell us about how our function is increasing, the second derivative can also tell us about how our first derivative is increasing. So we're going to work with some differentiable function. Let's say if f prime is increasing on a to b, then we say that f is concave up on a to b. So let's look at what this actually looks like. A graph which is concave up, you think about the graph of y equals x squared. If I steal this from Professor Keep, he says concave up like a cup, and I think that that's a good way to remember it because you have sort of this cup-like shape here. But if I were to sketch in tangent lines here. So here it says f prime is increasing. Remember, f prime tells us the slope of the tangent line. I'm going to sketch in a few tangent lines here, and I'll start maybe right here. There I have a tangent line, and I can look at that tangent line and say, well, the slope of that tangent line is negative, that line is decreasing. So okay, my slope is negative. If I move a little bit further to the right, maybe if I move to the vertex here, now I have a slope of 0. So let's actually just write this out. Here my slope is negative, here my slope is 0, and then if I pick another point over here, let's say, here I have a positive slope. Now my slope is positive. So the slope of all of these tangent lines are changing. They're going from negative to 0 to positive. In other words, they're increasing. And I can even continue to pick points over here on the right-hand side even further. I'm still going to have a positive slope right here. I'm still going to have a positive slope for that tangent line, but I can actually look at that slope and say, you know what, that line is steeper, which means I have a greater slope. So the slope of my tangent line is increasing yet still. So that's another way to say that f prime is increasing. So that's what it looks like when we have something which is concave up. So it doesn't necessarily need to be that whole parabola shape. You might just have a piece of that. So you might just have, if you think about like the exponential function e to the x is concave up, or you might have the exponential decay function. You might have something that looks like this. This is also concave up. So all of these graphs over here, these are concave up. And then similarly, if f prime is decreasing on that interval a to b, then we say that f is concave down on a to b. So again, we can draw a graph which is concave down. You can take that parabola and just sort of flip it upside down. So here let's take the graph of, say, negative x squared, just to pick one. And if I were to sketch in different tangent lines here, let's look at this tangent line. Well, the slope of that tangent line is positive. If I look at the vertex right here, my slope is 0. So I've gone from a positive number to 0, means my number is decreasing. And then after that over here, if I pick a number on the right-hand side, I have a line with a tangent line with a negative slope. Here my slope of the tangent line is negative. So I'm going from a positive number to 0 to negative. The slopes of these tangent lines are decreasing. So that's what a graph, a concave down graph would look like. Again, you don't need that whole shape necessarily. If you have the whole shape, cool, that's great. But I might also only have kind of a part of it. So rational functions will see this quite a bit. We might have something that looks like this or something that looks like this. So these are all concave downward. Finally, if f is continuous at some point c and f changes concavity at c, then c is called an inflection point of f, or sometimes I'll call these points of inflection. So these are points where my graph changes from being concave up to concave down. And you might see, we've actually seen a few of these. A lot of times we we've seen these with, say, the cubed function, right? If I look at y equals x cubed, you have this point in the middle where you have this horizontal tangent line. And actually, if you were to look at on the left-hand side, here on that left-hand side, it's concave downward, and then on the right-hand side, it's actually concave upward. This point right here is a point of inflection. These are, I think, a little bit harder to pick out than your local extrema. These are a lot more subtle. I think local extrema almost jump off the page at you, and it's easier to pick them out. But when we look at inflection points, they're not quite as obvious. So we're going to have to be a little bit careful. Really, the one thing that we can rely on, though, is our test for concavity here. So suppose that f double prime exists on some interval a to b. If f double prime is greater than 0, then f is concave up on a to b. And this should hopefully make sense here. F double prime is greater than 0. That's just the derivative of the derivative. So this is just another way to say f prime is increasing. So if the second derivative is positive, then our graph is concave up. Similarly, if f double prime is less than 0, so if our second derivative is negative, then the graph of f is concave down on a to b. And then just to reiterate here, if c is a point where f double prime changes sign, then f has an inflection point at c. So one note about inflection points, when we were looking at local extrema, we cared about are we changing from negative to positive or positive to negative, because that determined whether we had a local maximum or a local minimum. When we're working with points of inflection, we don't really care whether we're changing from negative to positive or positive to negative. All we need to see is a sign change in our second derivative. That's all we're going to be looking for. And as soon as we find that sign change, that tells us, oh, we have a point of inflection at this particular x value. So we don't distinguish the two separate cases. Just as long as there's some sort of sign change that we've established, then we can say that we have a point of inflection. So let's look at a couple of examples here. First, I want to just make sure we understand kind of what the graphing concave up and concave downward functions looks like. So here, we're going to see this quite a bit in this section and in the next section. So now we've got information about the first derivative and the second derivative as well. So I'm actually going to create two separate sign charts here. I'm going to create one for my first derivative, and I'm going to create one for my second derivative, because the signs of the first derivative and the second derivative may not always be the same. So let's see, we're changing sign, it looks like here at 0, so we've got 0 as an important point right here. Let's see, f prime is less than 0, so we're saying f prime is negative, and f double prime is greater than 0, so our second derivative is positive, on negative infinity to 0. So we're talking about this leftmost interval over here. So we said, first of all, f double prime is less than 0. It's negative, so our first derivative is negative, which means our function is decreasing on that interval. And then we also said f double prime of x is greater than 0 on that same interval. So I'm going to put some little positive signs right there so I know that, hey, the second derivative is positive. And then the other thing I like to do, I like to draw in a concave up function. Again, just so that I remember kind of the general shape of what I should be looking at is. And then, okay, now we have some different behavior on 0 to infinity on the right-hand side. Then f prime of x is greater than 0, so f prime is positive. So our first derivative changes sign from negative to positive. Our function is increasing here. And f double prime of x is still greater than 0. It's still positive. So our second derivative is still positive, which means our function is still concave upward on that interval. And this should give us enough information to sketch a function that looks like this. It doesn't say that it should be continuous, but I think that's probably the easiest way to sketch this function. So, okay, here's our coordinate axis. So now we just need to decide, okay, what does this look like on each side? And actually, I might look at the first derivative right here and just see, okay, do I have any local extrema? Well, yeah, I sure do. Look here, I'm changing from negative to positive at 0. So at 0, I should have, at this point right here, this is a local minimum here. However, I don't have any points of inflection because my second derivative is not changing sign here. It's positive on both sides, so I have no inflection points. But I do have a local minimum. So now I need to decide what this function looks like. I would recommend on each side, I think some students have trouble kind of bringing together the idea of increasing and decreasing and concave up or concave down. So what I would recommend is I would actually split this up. I'm going to look at each side of 0, and we'll do that down here. And first I'm going to draw, I know that my function should be concave up. So I always like to draw out a function which is concave upward. What else is my function doing? Well, my function is decreasing on this side over here. So I'm going to look and decide, well, which side of this function is decreasing? It's this left-hand side over here. So I'm going to just erase that right-hand side. Because that's really this is now the general shape of my graph on that left-hand side. It should look something like, let's say this. And again, where you place these y values isn't terribly important. Really, it's the x values that matter more than anything. I'll do the same thing on the right-hand side. So again, my graph is still concave upward. So I'm going to draw the graph which is concave upward. And I want the part of that graph which is increasing now. My function should be increasing. So here, this time, the right-hand side of my function is increasing. So I'm going to erase that left-hand side. That's not the side I want. And so it should have this kind of upward-facing curve, kind of oriented upward, and we see this parabola-like shape. You can sort of check your work here by taking these two and almost just connecting the dots between those two. What should they look like? Well, it should look like a parabola. So here we go. We have this parabola that has a local minimum, and we can check, hey, do we have that local minimum at 0? Yes, we do. So this looks good to go. We'll be doing problems like this a lot in the next section. In the next section, we're taking all of this information and saying, okay, how can I put all this together and graph our functions? So that's a really, really cool section. It's one of my favorite sections. But we'll be working with these number lines a great deal going forward in the next section. Let's look at a couple more examples here, some algebraic examples. Here I would like to identify the intervals where each function is concave up or concave down and find the inflection points. And we'll actually see that the actual mechanics, the process of solving these types of problems is really similar to the problems that we were doing earlier with determining where our function was increasing or decreasing and finding the local extrema. Really, the only difference is, because now we want to talk about concavity and inflection points, we're going to be repeating most of that process with the second derivative rather than the first derivative. So if all I'm concerned with is concavity and inflection points, I need the second derivative. So first I got to find my first derivative. F prime of x is equal to negative 4x cubed minus 6x squared plus 24x. There's my first derivative. Now I need my second derivative. So f double prime of x is equal to negative 12x squared minus 12x plus 24. So I have my second derivative, and just like we did with the first derivative, I want to find the partition numbers of that second derivative. So I want to find places where f double prime of x is equal to 0 and places where f double prime of x is undefined. So we'll take this case first, places where the second derivative is equal to 0. I'm going to start off, I already look at this and I say, boy, it would be nice if my leading coefficient was positive and if I factored out a negative 12. I'm going to do both of those things right away. So I'm going to factor out negative 12. That'll leave me with x squared plus x minus 2 is equal to 0. And then I can continue. Let's see, we can factor. This is really x plus 2 times x minus 1 is equal to 0. I end up with x equals negative 2 and x equals 1. These are two of my partition numbers. So these are going to be the numbers that I include on my number line, but now, again, since I'm talking about concavity, this number line is going to be for my second derivative rather than my first derivative. Just like we did with the first derivative in those last problems as well, I also want to think about places where f double prime is undefined here. And in this case, again, look at your f double prime. Here we have a polynomial, so f double prime is a polynomial. It exists everywhere. We're not going to have any extra partition numbers with that case. So I found my partition numbers. I'm going to now construct a sign chart for my second derivative. So we said we had negative 2 and positive 1. And just like we did with our first derivative, I'm going to take a number in each one of these intervals and plug those into my second derivative, because now I'm interested in knowing where is the second derivative positive and where is it negative. So let's see, I need a number on the left-hand side of negative 2. How about negative 3? I will plug that into my second derivative, f double prime of negative 3. This is equal to negative 12 times negative 3 squared minus 12 times negative 3 plus 24. And here we'd go and crunch some numbers here. Let me do this really quickly. I should have a negative 48 coming out of that. So it's negative. Again, we'll put some minus signs there, and I'll also draw the graph of a function which is concave down right above it. Next, I need a number that's between negative 2 and 1. How about 0? I always like to work with 0. F double prime of 0. This is negative 12 times 0 squared minus 12 times 0 plus 24. I should end up with a positive 24 here. So my function, my second derivative is positive, which means that my original function is concave upward between negative 2 and positive 1. And then I need a number to the right of 1. How about positive 2? F double prime of positive 2. This is equal to negative 12 times 2 squared minus 12 times 2 plus 24. And this time I come up with negative 48 once again. So it's negative on that right-hand side, which means that my function must be concave down. Again, at this point now, most of my work is done at this point. I have this sign chart right here, which has all of the important information. I have just a couple small steps here at the end. So first of all, let's talk about where our function is concave up or concave down. Our function is concave up on this middle interval right here between negative 2 and positive 1. So it's concave up on negative 2 to positive 1. It is concave down on negative infinity to negative 2 and 1 to positive infinity. So it is concave down negative infinity to negative 2 and 1 to positive infinity. The other thing I need then is my inflection points. Where is my second derivative changing sign? Well, it changes from negative to positive right here at negative 2, and then it changes from positive back to negative here at 1. So the last thing I need are the inflection points. I have the x values. Remember, these are both x values over here. I just need to find the y values. I look at my original f of x right here. That is where I look for my y values. I'm going to take those x values, plug them into my original function, my original f of x, and that will tell me the y values. Let me do that in red. So I have inflection points. Let's see, f of negative 2, and this is opposite negative 2 to the 4th, minus 2 times negative 2 cubed, plus 12 times negative 2 squared. I'm running out of room, I apologize. But there I should end up with a positive 48. And then I'll do the same thing with f of 1. So this time again, I'll plug it into my original function. I'm not going to write it out because I don't really have the room. I'll end up with 9. So I'll have 2 inflection points, negative 2, let's even that out a little bit, negative 2 comma 48 and 1 comma 9. F of negative 2 is equal to 48 and f of 1 is equal to 9. Those are my inflection points. You can write your answer like that, or of course if you wanted to write an ordered pair, negative 2 comma 48 and 1 comma 9, that would work just as well. So these are the inflection points, and then we have our concavity. This is everything that the problem asked us to do. We're done with this one. So hopefully this feels really, really familiar to the problems that we were doing in the last section when we were talking about the first derivative test. We're essentially repeating a lot of this same process. We're just using the second derivative instead of the first derivative.